based on Toby Glocker's slides. And here we have the, um, the ability to calculate the closing speed and delta V. Okay, what are we talking about? Closing speed would be the speed at which the collision starts, and delta V would be the change of the original velocity after the collision. The change from that original velocity is delta V. But we need to talk about delta V in terms of vectors, obviously. So these are the he is citing the comparison of the results obtained in different analytical techniques for reconstruction of highway accidents from this paper. Um, okay, here an example. This collinear low-speed collision. Low-speed collisions are an interesting phenomenon because um, you want people tend to think that you have to have a high-speed collision to get injury, and actually there are low-speed collisions that produce injuries. All right, that's important to know. And remember, low-speed collision could occur in the elastic range. What does that mean in terms of the energy? Huh? It's conserved. You see, so it depends on what was injured, what the level of injury was. It could be even not enough to trigger off the EDR, the airbag control module or computer that records the crash pulse, but could still cause injuries. So you have a collinear low-speed collision. There's your vehicle, and there's the other vehicle that apparently was hit on the back, but you can hardly tell damage in there. At the moment, you can see some scratches. All right. This, I want to show you, this graph that you see comes from the airbag control module. Um, this is the timing milliseconds. See? Do you see how small this is? This is a but do you see how it occurs 4 miles an hour? Mm. Again, delta V is there. It says longitudinal delta V is in the direction that the collision occurred. Right? Here, research on these vehicles, on these two examples, reveal this following stiffness values for the Toyota. Remember now those values are the stiffness values that the NTSA publishes based on test data, and B0 was the speed at which no damage occurs. So then we have the same data for the other vehicle values for no, these are for the Toyota. Weight 3,000 pounds. Weight of the Audi 3,900 pounds. So it says this is important based on the license plate imprint on the rear of the Audi. Assume the vehicle overlap is 50% of the wider L73. Research revealed no rear impact testing exists for the Audi or its sisters or clones. So in this case, you can use class values. Mm. This is important because you could be asked by, if you're on a deposition or trial, um, whether your opinion is based on data that is flaky. I mean, and the defense attorneys are going to be very sharp about that. And there's no flaky data by saying that you follow the procedure when you don't have this specific car with this specific problem on an NTSA list of available data. It is a standard practice to when that doesn't exist, take the class of vehicles and find out those coefficients. So if you plug this in here in the spreadsheet that I show you, I think one thing that I gave you that spreadsheet, that was part of what's in the on temp. Toby has several of these to be able to help us implement those calculations. So there are all these equations that have been calculated on the PDOF. Okay, so I just wanted to remind you, these are the other equations. This is what he's talking about. Let's see. Oh, he's got a lot more. Hmm. This is very helpful. It's a very important data for you. Uh, okay, let's go back to this. Okay, we have another low speed collision. So he's showing you here to using the spreadsheet to calculate the delta V. Here would be also a low speed collision. Dodge back into the Toyota at a traffic light. This is the Dodge, or this. Let's see, which one is this? Yeah, this is the Dodge. So in this case, the Dodge backed into the stop Toyota. So it was reversed. Okay, Dodge backed into the stop Toyota while waiting at a traffic light. And actually can happen because if the front driver, he went over the line, he realizes the mistake, there's a camera in there, he backs up quickly and hits the car behind. Um, Dodge 4,400 pounds, Toyota 3,900. So the question is, problem says research reveal unreliable rear stiffness coefficients for the Dodge using class values. This is the data from the EDR. he's showing us again how to use those formulas and the spreadsheets for making a practical calculation here. Okay, so that's the point, to use those spreadsheets to apply based on the data that you know. And this one even using data from the EDR. Okay, let's talk about Newton's third law. It says that whenever a body exerts a force on another body, the second body will exert a force on the first. Same magnitude but opposite direction. Alright. In this particular case, the force on each vehicle is calculated by this expression in terms of the A and B coefficients. Okay, calculate the new value of H, it says. The new B, the new A. So here's an example. Rear impact test, 35 miles an hour. That's not too slow. 35 miles an hour is 10 miles over to what you drive in the city. So in this case, you're getting data from the EDR. These little tables, they come from the airbag control module. The EDR is the computer, and the storage space that is inside the airbag control module. So here's what we have. Cadillac DeVille, an impact on this other vehicle. Okay. So here's the collision. So here we have 1993 Cadillac DeVille, 3,900 pounds. The dimension 73 times 60 inches. The crash, so you can measure there. Okay, then you have the other. Well, you have measured the crash. 1, 2, 3, 4, 5, 6. Okay. So use the test overhead photograph to estimate the Cadillac crash depth on the stiffness scales. This is nice because what he's suggesting is to use photogrammetry, meaning with a drone you could take a picture of your vehicle from the top and then in software measure the deformation. So the idea is to calculate the average depth. Okay, to calculate the average depth of the system, and With this, you can calculate the, or rather using the A and B values, come up with the associated energy and the equivalent barrier speed of 19 miles per hour. Now we can use the force from the Cadillac to calculate the adjusted A and B values for the Jeep. Why is this possible? The idea is that if you know the data and is precise for one car, by knowing the dimensions of the other vehicle, by knowing something about that, you can have this, done correctly. So these are more pictures from the test from there. Okay, so this is, you could review this on the spreadsheets that I gave you to verify these results. But the author is showing us how to use it here. Now this is also an important conclusion from the two vehicle collisions, and that is that when the other vehicle crashes, in this case into another, the question is, where is the force that caused this damage? Okay, and what you see in here is that um, on this diagram you see that if the collision occurred here, they inflicted a delta V of this magnitude. Or if you calculate delta V, the PDOF is immediately calculated because the two vehicles have an interaction between them. Yeah. Okay. There is a concept in here to alleviate this, this compensation for the this is to alleviate what I'm trying to say. There is an effective mass coefficient that takes care of the radius of gyration. Using the radius of gyration and the moment arm of the resulting force to the line of action. And calculate the radius of gyration by a square plus a square over 12 is just a rectangular shaped vehicle. I have shown you this example. Oh, no, I haven't shown you this example yet. This is a vehicle that is not at all. I think it's it. What did it say it was? Toyota. So we're gonna look for the broadside collision, and you're given the data here like this. We have good stiffness values for both vehicles. Let's see. So like, yeah, this is the other vehicle, and on the measurements, you see how much crash it has into it. Right? Calculate the force associated energy of the Honda. We calculate the force associated with energy of the Ford. Using his spreadsheets. Yeah, they are in that file that I gave you. And he uses these equations to calculate delta V1 and delta V2. The equations of conservation of momentum. Remember how this was derived? It says that V1 plus M1 plus M2 times V2 is equal to M1 times B prime 1 plus M2 B2 prime. So that's what you see here. I think this can be very helpful if the data says, yeah, it says was chasing by a police car. I think it was, if you have data like that, it could be the part of the accident here.
The projector should not.
Hmm?
Projector.
Oh. Okay. So basically the message is that there are equations that have been developed with the conservation of momentum and also with the data from the energy published by the NTSA. These are the reference cited on this work, and of course these papers you can get them on the library or from the SAE, the Society of Automotive Engineers. Um, Even the original Campbell paper is in here. The Mori paper also. Okay, got this. Okay.